tonight, deep beneath Europe, something happened that sounds almost too strange to belong to the physical world we know. At CERN, researchers have spent decades building machines capable of recreating conditions that existed for only fractions of a second after the birth of the universe. Particles are accelerated to extraordinary energies, smashed together, and reduced to traces in detectors. Most of the time, those traces confirm what physicists already expect. But every so often, nature leaves behind something different, a pattern, a state, a behavior that refuses to fit neatly into the framework scientists have spent generations constructing. And that is where this story begins. Because if CERN has genuinely identified a previously unknown quantum state, the interesting question isn't simply what they found, it's why it exists. Quantum physics already describes a world that seems almost impossible by everyday standards. Particles can behave like waves. Empty space is not truly empty. Fields fill the universe, and what we call particles can emerge as temporary excitations within them. Yet even this strange framework has boundaries. There are observations we understand. There are observations we can calculate. And then there are observations that make physicists stop and ask whether the picture itself is incomplete. Think about that for a moment. Imagine discovering a new kind of weather inside a climate model that was supposed to describe every possible storm. The storm isn't merely unusual. The equations themselves don't know what to do with it. That is the kind of possibility surrounding this discovery. But before we call anything impossible, we need to slow down. What exactly did CERN observe? What does physicists mean by a quantum state? Could the signal have another explanation? And if the observation survives every test, what would it actually mean for our understanding of matter? Because the most unsettling discoveries in physics rarely arrive with a dramatic announcement that everything is wrong. They begin much more quietly, a strange signal, a statistical excess, a pattern appearing where no pattern should be, and then someone notices it. If you enjoy this journey, like and subscribe. It helps more than you know. Now, let's go back to the beginning, before the strange state, before the anomaly, before CERN's detectors recorded anything unusual. Because to understand why a new quantum state could matter, we first have to understand the remarkably successful universe that physicists thought they already understood. There is a peculiar confidence built into modern physics, not the confidence of people who believe they know everything. Almost the opposite. Physicists know how much they do not know, but they also know that the part they do understand works remarkably well. The equations of quantum mechanics have survived experiment after experiment. The standard model of particle physics has predicted particles, interactions, and measurable quantities with astonishing precision. At CERN, beams of particles can be accelerated, collided, and studied under conditions that would be impossible anywhere else on Earth. And when the detectors record the aftermath, the results usually fall into place. A particle appears, a decay occurs, a predicted distribution emerges, the mathematics and the experiment meet. That agreement is one of the great achievements of science. It is also what makes a genuinely unexplained quantum state so interesting, because a strange result is not automatically a revolution. In physics, the first reaction to something unexpected is usually skepticism. Could the detector be wrong? Could the background have been underestimated? Could the statistical fluctuation simply be unusually large? Could an old theory explain the observation after all? Those questions are not obstacles to discovery. They are part of discovery. And CERN exists, in part, because answering those questions requires experiments powerful enough to push nature into places we cannot reach with ordinary technology. To understand what a new quantum state could mean, we have to begin with the strange world CERN was built to investigate, not with the collision, with the universe itself, because everything around you looks solid. The desk beneath your hands, the screen in front of you, The walls of the room, your own body. At human scale, matter seems straightforward. Objects occupy space. They have weight, they collide, they break, they move, but keep shrinking. Imagine taking a grain of sand and dividing it again and again and again. Eventually, you leave the familiar world of chemistry and enter the domain of atoms. Atoms themselves are not indivisible. Inside them are electrons surrounding a tiny nucleus. Inside that nucleus are protons and neutrons, and inside protons and neutrons are quarks. The deeper physics becomes less like a collection of tiny billiard balls and more like a landscape of invisible fields. This is where quantum theory begins to change the rules. At microscopic scales, nature does not always behave according to the expectations we develop from everyday life. A particle can possess properties that cannot be described, as though it were simply a miniature object sitting in one definite place. The act of measurement matters. Probabilities become fundamental. Energy comes in discrete amounts, and empty space itself turns out to have structure. That last idea is particularly important. The vacuum is not simply nothing. In quantum field theory, fields are present throughout space. The electron field, the electromagnetic field, the quark fields, the Higgs field. What we call a particle can be understood as an excitation of one of these fields. A useful analogy is an enormous ocean. From far away, the ocean looks like one continuous surface, but waves can rise and travel across it. The wave is not a separate substance from the ocean. It is a particular state of the ocean. Quantum fields work in a profoundly more complicated way, but the metaphor captures one essential idea. The particle is not necessarily a tiny object moving through an otherwise empty universe. It can be a disturbance in something more fundamental, and that brings us to the Standard Model. For all its complexity, the Standard Model is essentially humanity's most successful organized description of known elementary particles and three of the four fundamental interactions: electromagnetism, the nuclear force, the weak nuclear force. Gravity is notably absent. That omission alone tells us something important. The Standard Model is extraordinarily successful. It is not the final theory of everything. It cannot explain dark matter. It does not provide a quantum theory of gravity. It does not fully explain why the universe contains far more matter than antimatter. It leaves major questions about neutrinos, the Higgs sector, and the deeper structure of physical reality. But within the territory it covers, it works. And physicists take that success seriously. That is why new physics is difficult to establish. Imagine owning a clock that has kept time almost perfectly for generations. One morning, it loses 3 seconds. You would not immediately conclude that the laws of time had changed. You would inspect the gears, check the temperature, look for dust, measure the clock again, then again, and perhaps build another clock. Particle physics operates on the same principle. Except the clock is an experiment costing enormous amounts of engineering effort, and the 3 seconds might be a tiny excess buried inside billions of collisions. This is the environment in which CERN operates. The organization sits near Geneva, straddling the border between Switzerland and France. Its history reaches back to 1954, when European nations created an international laboratory dedicated to particle physics. The original vision was ambitious: use science to rebuild connections across a continent devastated by war. Then use increasingly powerful machines to probe the smallest structures of matter. Over the decades, CERN became one of the world's most important centers for experimental particle physics. And eventually came the machine that changed the scale of the experiment: the Large Hadron Collider, the LHC. A ring roughly 27 kilometers around, 27 kilometers. That is longer than many people travel in an entire day. Yet inside this enormous underground machine, 2 beams of protons can travel in opposite directions at speeds extremely close to the speed of light. They are not simply fired down a tunnel. They are guided by powerful superconducting magnets. The beam is focused, accelerated, steered, and eventually brought into collision at carefully selected points. The collision itself lasts an almost absurdly short amount of time. But the energy concentrated into those microscopic encounters can recreate conditions unlike anything experienced by ordinary matter on Earth. And that is the essential trick. If you want to discover something new, you need to create conditions where the new thing can appear. A telescope waits for distant light. A particle collider creates its own event. One looks outward, the other looks inward. And both, in their own ways, are trying to read the history of the universe. This is where CERN becomes more than a giant machine. It becomes a kind of laboratory for fundamental reality. The universe was once hotter and denser than anything we can naturally experience today. During its earliest moments, particles collided constantly. Energy was enormous. Matter and antimatter were produced and destroyed. Fields interacted under conditions that disappeared as the universe expanded and cooled. Modern colliders cannot recreate the beginning of the universe, but they can recreate certain aspects of the energy environment that existed during its earliest stages. And every time scientists push into a new energy regime, they are asking nature the same basic question. What happens here? Usually, nature answers in a familiar language. But sometimes, the answer is stranger. The most famous example from recent CERN history is the Higgs boson. For decades, the Higgs mechanism was central to the standard model, but the corresponding particle had not been directly observed. The LHC changed that. In 2012, CERN experiments announced the observation of a new particle consistent with the Higgs boson. The significance was enormous. It was not simply another particle added to a catalogue. It provided evidence for a mechanism that helps explain why many elementary particles have mass. And yet the discovery also revealed something about scientific progress. Finding the Higgs did not complete physics. It opened another door. Once the particle existed in the experimental record, researchers could begin measuring its properties. How strongly does it interact? How does it decay? Are its properties exactly what the standard model predicts? Every measurement became another test. And that pattern is repeated throughout particle physics. Discovery is rarely the final moment. It is usually the beginning of a much harder phase. Verification, characterization, comparison, challenge. That matters when we talk about a new quantum state. The phrase sounds definitive, but scientists use more cautious language. A signal can suggest a state. A collection of measurements can support an interpretation. A statistically significant observation can become evidence. And only after repeated independent confirmation does a scientific community begin treating an extraordinary claim as established. That distinction is crucial, because nature is full of things that look extraordinary before the full analysis is complete. A statistical fluctuation can imitate a discovery. A detector effect can resemble a particle. Two known processes can combine to produce an unexpected pattern, and human beings are exceptionally good at seeing meaning in patterns. Physics has learned to protect itself from that tendency through repetition, different analyses, different datasets, different detectors, different teams. The same conclusion appearing again and again. That is how uncertainty gradually becomes confidence. So when a CERN result appears to point towards something the existing framework does not comfortably explain, the first response is not celebration. It is suspicion. Good suspicion. Necessary suspicion. The strange signal must survive every mundane explanation scientists can find. And that is what makes the phrase quantum state so interesting. Because a quantum state is not simply a new type of particle. The term can refer to the complete quantum description of a physical system, the configuration of its relevant properties, energy, quantum numbers, and other measurable characteristics. In some systems, particles can combine into collective states. In others, fields can settle into unusual configurations. Matter can behave differently when squeezed, cooled, heated, or placed under extreme conditions. The quantum world contains phases of matter that have no obvious counterpart in everyday experience. Superconductivity is one example. At sufficiently low temperatures, certain materials can carry electrical current, with essentially no resistance. Superfluidity provides another. A fluid can enter a quantum state where its behavior becomes profoundly different from ordinary liquids. And there are exotic states that emerge only when enormous numbers of particles interact collectively. The word state, therefore, matters. A new quantum state might not mean that physicists discovered an entirely new fundamental particle. It could mean that known particles are behaving collectively in a way that reveals a previously unknown arrangement of matter or fields. That distinction will become increasingly important because the deepest surprises in modern physics do not always come from finding another brick. Sometimes they come from discovering that the bricks can arrange themselves into structures nobody expected. Think of a city. You can know every type of building in the city, every material, every road, every traffic rule, and still be surprised when millions of those components interact and produce something that cannot be understood by examining a single building. Quantum systems can behave in similar ways. The whole can acquire properties that are not obvious from the individual pieces. This is one reason the boundary between particle physics and condensed matter physics can become intellectually fascinating. Different experimental environments can reveal different manifestations of quantum behavior. At CERN, the energies are extreme. The timescales are microscopic. The systems are often created for an instant and then destroyed through decay. But the questions are universal. What is matter? What is a field? What counts as a fundamental object? And what happens when we push nature beyond the conditions under which our theories were tested? That final question is where the tension begins, because the standard model has passed extraordinary tests. But no theory should be confused with reality itself. A theory is a model, an extraordinarily powerful model, a map, and even the best map is not the territory. Scientists know this. They build theories precisely so that experiments can challenge them. A theory that cannot be tested is not doing the same job. A prediction that can be compared with observation is different. And if observation consistently refuses to match prediction, something has to give. Maybe the experiment is wrong. Maybe the calculation is incomplete. Maybe a hidden assumption was overlooked. Or perhaps the theory is missing something. That last possibility is the one that captures the imagination, because physics has changed before. Newton's laws transformed our understanding of motion. Then relativity showed that space and time themselves were not absolute in the way Newtonian intuition suggested. Quantum mechanics revealed that the microscopic world required an entirely different framework. Each revolution did not simply erase everything that came before. It contained the older theory within a broader understanding. Newton still works remarkably well for ordinary speeds and everyday scales. Quantum mechanics does not make your car stop behaving like a car. It explains why matter can behave the way it does beneath that familiar surface. That is how scientific revolutions often happen, not by destroying the old map, by discovering where the old map stops being accurate, and CERN exists near precisely that boundary. Every collision is another test. Every detector event is another clue. Every unexplained pattern is an invitation to look closer. The remarkable thing is that the universe does not care whether our theories are elegant. It does not care whether an equation has been accepted for 50 years. It does not care whether a result would be inconvenient. Nature simply does what nature does, and our job is to catch up. That is why the language surrounding possible discoveries can sound strangely restrained. Researchers may say a result is interesting. They may call it an anomaly. They may say it is consistent with a particular interpretation. Those words can sound underwhelming to the public, but behind them is an enormous amount of intellectual caution. Because the difference between an interesting anomaly and a genuine discovery can be the difference between one unusual dataset and years of independent confirmation. This is also why statistical significance matters. Suppose CERN conducts an experiment and finds a tiny excess of events in a particular energy range. At first glance, that excess may look meaningful, but if enough measurements are made, rare fluctuations will happen. Imagine tossing a coin thousands of times. Eventually, you might get an unusually long sequence of heads. That does not mean the laws of probability have changed. It means probability can produce strange-looking outcomes. Particle physicists, therefore, ask a harder question. How unlikely would it be to see this pattern if the known physics were correct? The smaller that probability becomes, the stronger the evidence. But even then, the analysis is not finished. Systematic uncertainties matter. Detector calibration matters. Background estimates matter. Theoretical assumptions matter. Independent confirmation matters. This is the slow machinery behind the dramatic word discovery. And somewhere inside that machinery is the possibility that a truly new state could emerge. A state that does not behave quite like the known states. A configuration whose properties cannot be reproduced by the standard calculations. A pattern that survives every attempt to explain it away. If such a thing exists, the question becomes much larger than CERN. It becomes a question about the architecture of reality. But we are not there yet, not even close. Before physicists can claim that a new quantum state has been found, they must establish something more basic. What exactly is being measured? Where does the signal appear? How often does it appear? What quantum numbers does it carry? What energy does it occupy? What does it decay into? And perhaps, most importantly, can the same behavior be reproduced? These questions transform an intriguing observation into a scientific investigation. And this is where our story begins to narrow. Away from the history of CERN, away from the broad success of the standard model, toward the moment when researchers begin staring at data and notice something that should not be there. The first clue may not look dramatic. There may be no flash, no visible explosion, no single event announcing that physics has changed, just a distribution on a screen, a curve, a cluster, a statistical excess, something slightly out of place. At first, it is easy to ignore. Then someone checks it again and again. The pattern remains. Now imagine sitting in that room. You have spent years studying the same equations. You know what the expected background should look like. You know what ordinary particle processes produce. And then you see a structure emerging where the familiar model predicts nothing unusual. Your first instinct is not, "We have discovered something new." It is, "What did we miss?" That question is the doorway. Because science rarely begins with certainty. It begins with discomfort. A result that refuses to settle. A measurement that keeps asking for another explanation. A small crack in an otherwise remarkably successful picture. And if the crack is real, the consequences can reach far beyond the machine that created it. They can reach backward into the earliest moments of the universe. They can reach downward into the structure of quantum fields. They can reach outward toward questions about what matter really is. But first, we have to look directly at the signal, not the headline, not the speculation, the measurement, because that is where extraordinary claims either begin to become evidence or quietly fall apart. And in the next part, we enter that uncertain territory, the place where CERN's detectors stop showing us the physics we expected and begin showing us something else. The most dangerous word in experimental physics is not impossible, it is obvious, because when a result looks obvious, there is a temptation to stop asking questions. A strange peak appears in the data. A cluster of events forms around an unexpected energy. A distribution refuses to match the background. And almost immediately, the human mind begins building a story around it. But CERN does not begin with the story. It begins with the event. A particle collision occurs. The detectors record what they can. And from those traces, researchers reconstruct what happened. That process is almost the opposite of watching an explosion. In an ordinary explosion, your eyes see light, smoke, fragments, movement. Inside a collider, the event itself is invisible. The collision happens on a scale far smaller than anything a human eye could resolve. What remains are signals inside layers of detector material, tiny electrical responses, energy deposits, particle tracks, timing information. From those fragments, physicists reconstruct the event afterward. It is less like watching a crime happen, and more like reconstructing an accident from tire marks, broken glass, security footage, and fragments scattered across a road. The event is gone. Only evidence remains. And that evidence is where a possible new quantum state would have to reveal itself. The Large Hadron Collider is built around this principle. Protons circulate through the 27-kilometer ring. Powerful superconducting magnets bend their trajectories. The beams travel in opposite directions. At designated interaction points, they are brought together. The collisions happen incredibly quickly, and most collisions are not what scientists are looking for. That sounds strange. The machine is designed to create extraordinary conditions, yet the majority of events are comparatively ordinary. This is because the physics being sought may be extremely rare. Imagine standing beside a waterfall and trying to photograph one particular droplet. You cannot simply point the camera at the waterfall and assume the important droplet will be obvious. You need enormous amounts of data. You need timing. You need filtering. You need reconstruction. And you need a very good idea of what ordinary droplets look like. Particle physics works in much the same way. The ordinary background matters because an unusual signal only becomes unusual in comparison with what should normally happen. This is why the Standard Model is not simply an old theory sitting in a textbook. It is part of the prediction machinery. Researchers calculate what known processes should produce. Then they compare those predictions with what the detectors actually record. The difference is where the interesting questions live. Sometimes the difference disappears. Sometimes it becomes a measurement of something already known. And sometimes, if the discrepancy survives enough scrutiny, it becomes an anomaly. That word sounds dramatic. Usually, it isn't. An anomaly simply means that something does not fit comfortably into the expected picture. It does not automatically mean new physics. It is a warning light. The engine might be failing, or the sensor might be dirty. You do not know yet, but you stop driving. That distinction matters enormously here, because headlines compress months or years of scientific analysis into a single sentence. CERN discovers new quantum state. The underlying research may be much more cautious. Researchers might actually be saying, "We observed a structure that may be consistent with a previously unrecognized quantum configuration." That difference is not semantic. It is the difference between evidence and interpretation. And interpretation is where the story becomes fascinating. Suppose the detectors reveal an unexpected concentration of events around a particular energy. What could that mean? One possibility is that a previously unknown particle or resonance has been produced. Another is that known particles have entered an unusual collective state. Another is that a familiar process has been calculated incorrectly. Another is that the detector response is introducing a subtle effect, and there is always the possibility of statistical fluctuation. The challenge is that several of these explanations can initially produce similar-looking patterns. Physics, therefore, becomes a process of elimination. Researchers change the selection criteria. They use different reconstruction methods. They examine different regions of the data. They compare independent detector systems. They test simulations. They ask whether the same pattern appears where it should not. They ask whether it disappears when a particular assumption is removed. The goal is not to make the signal look exciting. The goal is to make sure the signal survives attempts to destroy it. That is an unusual culture. Imagine trying to prove your own discovery wrong, not because you dislike it, because you want to know whether it is actually real. This is one of the strengths of experimental science. A beautiful idea has no special privilege. Nature gets the final vote, and CERN's detectors are designed to listen. The Large Hadron Collider contains several major experiments, including ATLAS and CMS, as well as specialized detectors designed for different questions. They do not all observe the same collisions in the same way. Their technologies differ, their analyses differ, their research programs overlap in some areas and diverge in others. That redundancy matters. If one experiment sees something unexpected, the most convincing future would be another experiment seeing the same thing independently. then the mystery becomes much harder to dismiss. This is how particle physics protects itself from false discoveries, and history has shown why that protection is necessary. There have been moments when tantalizing signals appeared to point toward new particles. Then more data arrived. The signal weakened. Eventually it disappeared. The universe had not changed. The statistics had simply been doing what statistics sometimes do. This is why physicists often seem frustratingly conservative. They have seen how easy it is to get excited too early. A 5 sigma discovery threshold became famous partly because particle physics deals with enormous numbers of events, and therefore enormous opportunities for random fluctuations. The precise meaning of statistical significance is more complicated than a headline can convey, but the basic idea is simple. If the known background would almost never produce the observed excess, the evidence becomes much more compelling. Yet even 5 sigma is not a magic stamp from the universe. It is a statistical statement under a particular model and analysis. Systematic uncertainties remain, independent confirmation remains, replication remains. The machinery of science continues. This brings us back to the strange state. If researchers believe they have identified a new quantum configuration, the crucial question becomes, what makes it different? A quantum state can be characterized through measurable properties, energy, momentum, spin, charge, other quantum numbers, and sometimes collective properties that emerge from interactions between many particles. The word quantum does not mean mystical. It means that nature at microscopic scales follows rules in which certain physical quantities can take discrete values or are governed by quantum probabilities. The mystery begins when those rules produce a state that does not fit the states we already know how to describe. Consider water. The molecules are familiar, H2O, but the same molecules can form ice, liquid water, or vapor. The molecules did not have to become new substances for the system to acquire dramatically different properties. The arrangement changed, the interactions changed, the phase changed. Quantum matter can be far stranger. Particles can become correlated, their behavior can become collective. Properties can emerge that do not belong to any individual particle by itself. In extreme environments, matter can enter states that would be impossible under ordinary conditions. So when physicists talk about a new quantum state, they may be describing a new organization of known ingredients. That is one of the most interesting possibilities, because it would mean the inventory of particles might not need to change for our understanding of matter to change. The same pieces could be capable of more than we realized. Now consider what happens at CERN. The collision energy is enormous, but the system is also incredibly short-lived. A state can appear and vanish almost instantly. Researchers may never observe the state directly. Instead, they infer its existence from the products it leaves behind. This is where particle physics begins to resemble archaeology. An archaeologist rarely watches an ancient civilization build a city. They find pottery, foundations, roads, tools, human remains. From those traces, they reconstruct a world that disappeared thousands of years ago. Particle physicists do something similar at an utterly different scale. The original state may survive for an almost unimaginably short time. Its decay products become the evidence. If the state existed, it should leave a recognizable fingerprint. And if the fingerprint is unusual, researchers begin asking what kind of state could have produced it. That is where the theoretical physicists enter the story. Experimentalists can say, this pattern is here. Theorists ask, what could produce it? The first explanation is usually conservative. Could known physics account for the observation? Perhaps a resonance was modeled incorrectly. Perhaps two processes overlap in a way that was not obvious. Perhaps the background contains a contribution that had been underestimated. Only after those possibilities are exhausted does the conversation move toward more exotic ideas. That is an important order. New physics is not the first explanation. It is the explanation that becomes interesting when ordinary explanations stop working. And this is where a supposed new quantum state becomes genuinely consequential. Because the standard model has an enormous number of successful predictions behind it. A new state must coexist with all of that success. It cannot simply explain one strange result while breaking everything else. A new theory has to do more. It must reproduce the old results where the old theory works. Then it must explain the new observation. This is why scientific revolutions are difficult. The replacement has to be better than the thing it replaces. It must inherit the successes, and it must explain the failures. That is an extraordinarily high bar, but it is exactly what makes the rare breakthrough so valuable. Now imagine that the unusual signal survives the first round of checks. The detector calibration is sound. The event reconstruction works. The background model has been tested. The pattern appears in multiple analyses. The statistical significance continues to increase as more data arrive. At this point, scientists cannot simply ignore it. They have to explain it. And that is when the language changes. The question is no longer, could this be an error? It becomes, what is nature doing? This is the transition from anomaly to mystery. And mysteries in physics have a special character. They are constrained. You cannot propose anything you want. The explanation has to respect conservation laws. It has to fit known quantum principles. It has to remain consistent with previous experiments. It has to predict something testable. A beautiful theory that explains nothing new is not enough. A strange theory that makes a prediction we can test is much more interesting. This is why researchers can spend years debating a result that appears simple. The detector may show a small bump. The paper may contain a handful of unusual distributions. But behind those graphs is an enormous theoretical landscape. One possibility might involve a new bound state. Another could involve an exotic arrangement of quarks. Another might involve a previously unrecognized interaction. Another could require physics beyond the standard model. And another may eventually turn out to be nothing new at all. The uncertainty is not a weakness, it is the scientific story. There is another complication. The word new can mean several different things. New to the experiment, new to the standard model, new to experimental observation, new as a theoretical possibility. Those are not equivalent. A state may have been predicted decades ago but never observed. Another may be completely unexpected. A third may be mathematically familiar, but appear under physical conditions nobody had previously achieved. Each possibility would carry a different scientific significance, and so researchers would begin with the most basic question. What exactly is the state? Is it a particle, a bound state, a phase, a resonance, a collective excitation, or merely a temporary configuration of known fields? Those words won't sound technical, but they represent radically different pictures of reality. A resonance, for example, can be thought of as a short-lived state that appears when particles interact at particular energies. It is like pushing a swing at the right rhythm. The system responds strongly. But unlike an ordinary swing, the quantum state may exist for an incredibly brief interval before decaying into other particles. If the decay products are unusual, the resonance can leave a fingerprint. A bound state is different. Quarks, for example, are never normally found as isolated objects under ordinary conditions because of the strong interaction. They can form composite structures. Protons and neutrons are examples of composite states built from quarks and gluons. But quantum chromodynamics, the theory describing the strong interaction, allows a rich spectrum of possible structures. Some may be extremely short-lived, some may exist only under special conditions, and some may reveal themselves only when experiments become sensitive enough. This is why the boundary between known matter and new matter can become surprisingly blurry. Nature may not respect the categories humans find convenient. We divide particles into names. Nature gives us fields, interactions, symmetries, and states. The names are ours, the behavior is not. That thought becomes especially powerful when considering the early universe. Immediately after the Big Bang, the universe was not filled with stars and galaxies. There were no planets, no atoms, no chemistry. The universe was an extraordinarily hot, dense environment dominated by particles and fields. As expansion continued, temperatures fell. Different physical processes became possible. Some symmetries broke, particles acquired properties, bound states formed. Eventually atoms appeared. Much later, stars ignited. The universe we see today is therefore the cooled aftermath of an enormous sequence of physical transitions. A new quantum state produced in a modern collider could, in principle, provide a small window into those ancient conditions. Not because CERN recreates the entire early universe, it does not, but because the fundamental rules governing matter are the same. That is the extraordinary bridge. A machine built by humans beneath the ground can probe physics that shaped the cosmos billions of years ago. And this is where CERN's story begins to touch the work of another extraordinary observatory. The James Webb Space Telescope looks in the opposite direction. Instead of accelerating particles inward, Webb looks outward through time. Its infrared instruments observe galaxies whose light has traveled for billions of years. Webb can examine ancient galaxies, star formation, dust, black holes, and the conditions of the young universe. CERN and Webb are therefore doing something complementary. One recreates extreme conditions in the laboratory. The other observes the consequences of cosmic history written into ancient light. Neither replaces the other. And sometimes the deepest scientific questions emerge when laboratory physics and cosmic observations begin pointing toward the same missing piece. If a new quantum state were confirmed at CERN, researchers would naturally ask whether its existence has consequences beyond the collider. Could related physics have existed in the early universe? Could it influence how particles formed? Could it leave an imprint on cosmic evolution? Could it help explain something astronomers have already observed? Those questions would require evidence, but they would be worth asking, because fundamental physics has always been connected across scales. The same equations that describe subatomic particles can influence the evolution of the cosmos. The smallest structures can shape the largest. That is one of the strangest facts in science. The universe does not have separate rulebooks for different sizes. There are different approximations, different effective descriptions, different regimes, but underneath them lies one physical reality. And if something new is happening at the quantum level, its consequences may not remain quantum forever. They could echo upward, into chemistry, into stars, into galaxies, into the history of the universe itself. But before we allow the imagination to run that far, there is a more immediate problem. The signal must survive, because there is a brutal stage in every potential discovery when the excitement has to be put aside. Researchers take the data apart. They change assumptions. They test alternative models. They examine every known background process. They search for independent signatures. They ask whether another detector can see the same thing. They try to make the mystery disappear, and if they fail, the mystery becomes stronger. This is the moment when the scientific community begins to pay serious attention. Not because someone says the physics is broken, but because the old explanation is becoming harder to maintain. The difference is subtle and enormous. Physics does not collapse because one experiment sees something strange. It changes when repeated observations force researchers to construct a better explanation. That process can take years, sometimes decades. The Higgs boson took decades of theoretical and experimental development before the 2012 announcement. The search for physics beyond the standard model is even broader. There are unanswered questions everywhere. Dark matter, neutrino masses, matter-antimatter asymmetry, quantum gravity, the nature of dark energy, the hierarchy of fundamental scales, the origin of the universe's initial conditions. A new quantum state would not solve all of these, but it could become another piece of the puzzle, and that is why researchers would treat it carefully. A single unusual state may tell us something very specific, or it may be the visible edge of a much larger structure. The difference cannot be known from the first observation. You need more collisions, more measurements, more energy, more precision, more independent analysis, and perhaps the most revealing test of all, try to make the same state again. If it appears repeatedly under controlled conditions, the story changes. If it appears at another detector, the story changes again. If its properties match a theoretical prediction, a new chapter opens, and if it refuses to match any existing explanation, then we have something much more profound. Not proof that current physics is useless, quite the opposite. Proof that current physics has brought us to a boundary, a place where its extraordinary success has finally revealed its own limits. That is how science moves forward. The old theory does not necessarily become worthless. It becomes a special case, a lower energy approximation, a map of one region, and beyond that region something new waits. But there is still one question hanging over everything we have discussed. What would a genuinely new quantum state look like if we could somehow see it directly? What properties would distinguish it from every known state? What kind of mathematical structure would be required to describe it? And what if the answer is not a new particle at all? What if the state is telling us something about the quantum vacuum itself? Because that possibility takes us somewhere much stranger. The vacuum is supposed to be the lowest energy state available to a quantum system, but lotus energy does not mean nothing. Fields still exist, quantum fluctuations remain, and the structure of the vacuum is deeply connected to the laws that govern particles. If experiments were to reveal an unexpected state associated with those fields, the implications could extend far beyond a single detector result. They could touch one of the oldest questions in modern physics. Is the world built from particles, or are particles merely the visible behavior of something deeper? CERN cannot answer that question with one collision, neither can any telescope, but experiments can narrow the possibilities. They can eliminate ideas, they can reveal structures, they can show us where the equations work, and where they begin to strain. And somewhere in that narrow region between prediction and observation is where a new quantum state would live. Not in the headline, not in the speculation, in the data. That is the place we have to follow next. Because if the signal survives, researchers eventually have to stop asking whether something unusual happened. They have to ask a much more uncomfortable question. What kind of physics could produce it? And when the first theoretical explanations begin to arrive, they do not all point in the same direction. Some remain close to established physics. Others reach toward exotic forms of matter, and some suggest that the standard model may be showing us the first visible edge of a deeper theory. The strange signal has survived long enough to become a problem. Now the problem needs an explanation. There is a moment in every scientific investigation when curiosity changes character. At first the unusual result is exciting, then it becomes interesting, then it becomes inconvenient. And eventually, if the evidence survives long enough, it becomes a problem that researchers can no longer politely set aside. That is where we are now. The question is no longer simply whether CERN saw an unusual pattern. The harder question is what that pattern could possibly mean. Because the standard model has an answer for an astonishing number of things. It describes known elementary particles. It describes how they interact through the electromagnetic, weak and strong forces. It predicts measurable quantities with extraordinary accuracy. And yet, despite all that success, physicists know there are cracks in the larger picture. Some are obvious. Gravity does not fit naturally into the standard model. Dark matter appears to exist, yet its fundamental identity remains unknown. Neutrinos have mass, but the simplest form of the standard model did not originally account for it. The universe contains overwhelmingly more matter than antimatter, and the known sources of asymmetry appear insufficient to explain the imbalance. Then there is the deeper problem. Why these particles? Why these masses? Why these forces? Why these particular values of nature's constants? The standard model tells us how the pieces behave. It does not fully explain why the pieces exist in precisely the form we observe. That distinction matters. A theory can be extraordinarily predictive while still leaving the deepest question unanswered. And that is why a new quantum state could be so valuable. Not because it would immediately overthrow physics, because it might provide a clue about what comes next. But there is a problem. Physics has learned to be suspicious of clues. A strange result can point toward new physics. It can also point toward a calculation that needs correction. This is where the theoretical battle begins. Imagine a locked room. Inside the room is an object you cannot see. You can only observe shadows beneath the door. One shadow is long, another is short, a third changes shape. Several explanations could produce those patterns. Maybe there is a chair, maybe a person is moving, maybe there are several objects. The shadows constrain the possibilities, but they do not reveal the object directly. Particle physics often works this way. The state itself may be too short-lived to observe. Its existence must be reconstructed from its consequences. And the first theoretical question is therefore brutally simple. What known process could imitate the signal? Researchers begin there because the known physics has earned that privilege. The standard model is not assumed to be correct because scientists are emotionally attached to it. It is assumed because experiment has repeatedly demonstrated that it works. So the first possibility is always some form of ordinary physics behaving in an unexpected way. Perhaps several known particles are interacting in a more complicated way. Perhaps an intermediate resonance has been misunderstood. Perhaps the theoretical calculation omits an effect that becomes important under these conditions. Perhaps the background estimate is wrong. Perhaps the detector sees one process slightly differently than the simulation expects. Every one of those possibilities has to be tested, and this process can be painfully slow. A physicist may spend months investigating what looks, from the outside, like one small discrepancy on one graph. That graph may contain millions of events. The difference may be less than 1%, yet that tiny difference could potentially contain the first clue to a deeper theory. This is why precision matters. The frontier of particle physics is not always reached by simply building a bigger machine. Sometimes it is reached by measuring a known quantity more accurately. If theory predicts a value to 10 decimal places and experiment consistently finds something different in the final digits, that discrepancy can become scientifically explosive. It is like discovering that a clock loses one fraction of a second every day. The amount is tiny, but if the error is systematic, it tells you something about the mechanism. The same principle applies to a quantum state. The details matter. Its energy, its lifetime, its decay channels, its charge, its production rate, its interactions. Each measurement narrows the possibilities. And this is where the phrase, "current physics can't explain it," must be handled carefully. In science, "can't explain" rarely means that researchers have no equations at all. It may mean that existing calculations do not naturally reproduce the observed combination of properties. That is a much more interesting statement. Imagine having a language with 1,000,000 words, then discovering a sentence that contains only familiar words, but cannot be made grammatically consistent. The problem may not be the vocabulary, it may be the grammar. In physics, the particles can be familiar while the organization of their interactions is not. This possibility brings us to quantum chromodynamics. The strong force is one of nature's fundamental interactions. It governs quarks and gluons, and it is extraordinarily complicated. Quarks carry a property called color charge, not literal color, a mathematical label describing how they participate in the strong interaction. There are 3 such color charges, conventionally called red, green, and blue, with corresponding anticolors. The names are convenient, the physics is not. Quarks are confined inside composite particles under ordinary conditions. They do not simply fly around independently in the way electrons can move through a vacuum. The strong interaction becomes stronger as quarks are separated. That makes the behavior of quark matter profoundly different from familiar electromagnetic systems. And because the strong force is so complicated, there may be many ways for quarks and gluons to organize themselves. Some structures are well established, others are exotic. There are hadrons made from 3 quarks, like protons and neutrons. There are mesons made from quark-antiquark combinations. And modern experiments have provided evidence for more complicated structures, including tetraquark and pentaquark-like states. These discoveries have already expanded our understanding of what matter can look like, but they also raise a deeper question. How many configurations are possible? Could the strong interaction create states we have not yet recognized? Could some apparently new particles actually be collective arrangements of familiar ingredients? This is one reason a strange quantum state does not automatically require a brand new fundamental particle. Nature may be rearranging existing ingredients. Think about Lego. You can build a house, then a bridge, then a tower, then something nobody had thought to build before. The number of pieces has not changed. The possible structures have. Quantum chromodynamics may be like a Lego system whose rules are so complicated that we have only discovered a fraction of its possible architecture. And this is where the word state becomes powerful. A new state could represent a new arrangement rather than a new fundamental ingredient. But there is another possibility. The unusual behavior could involve a new interaction. This would be far more consequential. The Standard Model describes 3 fundamental interactions among elementary particles. If a previously unknown force exists, its effects might appear as subtle deviations from expected behavior. A new interaction would not necessarily announce itself with a spectacular explosion. It could produce a small change in a decay rate, a slightly unusual angular distribution, a tiny excess in certain collision products, a weak coupling that becomes visible only at high energy. That is how new forces can hide. They do not need to dominate the universe. They only need to leave a measurable fingerprint. This is why particle physicists pay attention to rare processes. Rare events can be valuable precisely because the background is small. If a process almost never occurs under the Standard Model, even a small excess can become interesting. But rare also means difficult. You need enormous amounts of data, and the more you search, the more opportunities you create for statistical accidents. That is the paradox. More data gives you sensitivity, but more data also gives random fluctuations more chances to appear somewhere. So researchers have to correct for the fact that they are often searching across many possible energies, decay channels, and variables. This is sometimes called the look elsewhere effect. Imagine scanning a beach for one unusually shaped shell. If you inspect one shell, finding a strange one might be surprising. If you inspect 10 million shells, eventually one will look bizarre. The fact that it looks bizarre is not enough. You have to ask how surprising it is, given the number of places you looked. That is one reason extraordinary claims require extraordinary statistical discipline, and it is also why a genuinely persistent anomaly is so valuable. If a signal keeps appearing in independent analyses across different datasets with consistent properties, the probability of coincidence begins to fall. The mystery becomes harder to dismiss. Now imagine that the strange state has survived those tests. Its properties are measured. Its production mechanism is investigated. Its decay products are consistent. And its behavior still does not fit the Standard Model comfortably. The theoretical community now faces a different problem. What theory can accommodate it? Several broad possibilities emerge. One is that the Standard Model is incomplete but remains embedded inside a larger theory. This is actually the most likely conceptual structure if new fundamental physics is discovered. Newtonian mechanics did not become useless after relativity. It became an approximation. Likewise, the Standard Model could remain extraordinarily accurate within its tested domain, while becoming one layer of a deeper framework. That deeper framework might involve new particles, new symmetries, new dimensions, new interactions, or entirely different principles. But these ideas must be treated cautiously. Theoretical physics contains an enormous number of possibilities. A paper can propose an elegant explanation within days of an unusual result. That does not mean nature chose that explanation. The universe does not reward mathematical beauty. It rewards accurate prediction. The only way forward is experiment. This is why the next measurement matters more than the first interpretation. If one model predicts that the new state should interact strongly with a particular particle, researchers can search for that interaction. If another predicts a specific decay pattern, detectors can look for it. If a theory predicts that the state should appear at another energy, the collider can test that region. The strange state becomes a machine for generating questions. And this is one of the most beautiful things about physics. A discovery does not simply answer questions, it manufactures better ones. The Higgs boson is a perfect example. Finding it confirmed the mechanism associated with electroweak symmetry breaking, but it immediately created new questions. Why is the Higgs mass what it is? Is the Higgs sector minimal? Are there additional Higgs particles? Could the Higgs connect to dark matter? Could the Higgs field contain clues about the early universe? A successful discovery opens doors. A new quantum state would do the same. But now consider the possibility that the state is not simply another particle. What if it is collective? That possibility takes us into a deeper layer of quantum theory. At everyday scales, properties often belong to individual objects. A single ball has a velocity. A single battery has a voltage. A single atom has energy levels. But in quantum systems containing many interacting particles, collective behavior can emerge. The system can act as something larger than the sum of its components. Superconductivity is one example. A large number of electrons can enter a correlated quantum state in which electrical resistance essentially disappears. No individual electron suddenly becomes magical. The collective state behaves differently. Superfluidity provides another example. A fluid can acquire properties that emerge only from the coordinated quantum behavior of many particles. The same principle appears across condensed matter physics. And although the conditions at CERN are radically different, the conceptual lesson is universal. The universe can produce new behavior without introducing new ingredients. Sometimes the new thing is an arrangement. Sometimes it is a phase. Sometimes it is a collective excitation. Sometimes it is a resonance. And sometimes it really is a new fundamental particle. Distinguishing among these possibilities requires more than observing an anomaly. It requires characterizing the state. That means asking how it responds. How long does it survive? How does it interact? What does it decay into? Can it be produced in another way? Does it have a partner? Does it obey the symmetries we expect? Does it violate any? And perhaps the most fascinating question, does it connect to something else we have already observed? Because physics rarely leaves one unexplained phenomenon sitting alone. If a new state is real, it may belong to a larger family. A single particle can be the visible member of an entire sector. A new interaction can imply additional particles. A new symmetry can produce new conservation laws or partners. A new phase can indicate a larger structure of quantum matter. The first discovery may therefore be only the first piece. This is how the scientific frontier expands. One strange observation becomes a map of unexplored territory. But there is an even deeper problem. The standard model is quantum. General relativity is not, at least not in its conventional formulation. And these two pillars of modern physics do not fit together cleanly. Quantum mechanics describes microscopic reality with extraordinary success. General relativity describes gravity, space-time, stars, black holes, and the large-scale structure of the universe. But when both theories are pushed to extreme conditions, the mathematics becomes problematic. Inside black holes, near the earliest moments of the universe, at the Planck scale, there, our current frameworks appear incomplete. A new quantum state would not automatically solve quantum gravity, but any new fundamental phenomenon is potentially relevant to the search for a deeper theory. That is why physicists care about anomalies even when they seem narrow. The small can point toward the enormous. A tiny deviation in a particle experiment could eventually tell us something about the structure of the universe. This sounds grand, but the connection is real. Consider the Higgs field. Its behavior is tied to the structure of the vacuum, and the vacuum is not merely an empty background. The vacuum determines which particles can exist in which states. It influences masses. It affects quantum fluctuations. It is part of the structure from which ordinary matter emerges. So, if a new quantum state reveals unexpected behavior in a field, the implications could extend beyond the particle itself. It could force researchers to reconsider assumptions about the vacuum. And that would be profound, because the vacuum is everywhere, not just inside CERN, not just inside a detector, everywhere, in your room, between planets, inside galaxies, across intergalactic space. The same quantum fields that scientists manipulate indirectly in a laboratory exist throughout the universe. A laboratory discovery can therefore become a cosmic question. What if the state existed naturally in the early universe? What if it formed when temperatures were unimaginably high? What if it affected how matter cooled? What if traces of it remain hidden in ancient radiation? This is where particle physics meets cosmology. And this is where the James Webb Space Telescope becomes relevant again. Webb cannot directly detect a quantum state created in a collider. Its instruments are designed to observe infrared light from astronomical objects. But Webb can see the consequences of early universe physics. It can observe galaxies whose light has traveled for more than 13 billion years. It can study how rapidly stars formed in the young universe. It can investigate massive black holes in surprisingly early galaxies. And when observations challenge our expectations about cosmic history, physicists naturally ask whether the underlying particle physics might be involved. The connection is not proof, it is a bridge. A laboratory experiment can reveal the rules. A telescope can reveal the consequences. And sometimes the two directions meet. This is why modern physics increasingly feels less like separate subjects. Particle physics, cosmology, astronomy, quantum information, condensed matter, they overlap. Different experiments interrogate different scales of the same universe. The strange quantum state, if confirmed, would enter that network. But there is still one enormous obstacle. The standard model has not failed spectacularly. It has failed quietly. That may sound contradictory, but it matters. There is no single observation that says, the standard model is wrong. Instead, there are unanswered questions, persistent anomalies, missing ingredients, phenomena it cannot explain. The theory remains remarkably successful within its domain. So a new state would have to fit into this strange landscape. It would not be replacing a broken machine. It would be modifying an extraordinarily functional one. That makes the task harder and more interesting. Imagine discovering a previously unknown room inside a building that has already been mapped down to the centimeter. You do not immediately demolish the building. You ask how the room connects to the existing structure. Where is the doorway? Why was it missed? What else might be behind the walls? That is the intellectual position physicists would face. The new state would become an entrance. But into what? A new family of particles? A hidden interaction? A deeper symmetry? A new phase of matter? Or something more fundamental than particles themselves? There is no way to know yet. And that uncertainty is exactly where science becomes most alive. Because if the answer were already known, there would be no mystery. The next step is measurement. More precise measurements, more collisions, different collision energies, different production mechanisms, independent experiments, theoretical calculations, and perhaps new machines in the future. CERN's present accelerator program is not the end of particle physics. It is part of a much longer trajectory. Future colliders have been proposed and studied. Some would be larger. Some would prioritize precision. Some would collide different types of particles. The goal is always the same: push the boundary, create conditions where hidden behavior becomes visible. The strange state therefore raises a practical question. If it is real, can CERN produce it again? And if CERN can produce it again, can researchers manipulate it? Can they measure it more precisely? Can they determine its quantum numbers? Can they discover what it interacts with? Can they find related states? The first observation might be the hardest, but understanding the state could be harder still. This is where the mystery becomes more dangerous. Because a new state does not tell you what theory should replace the old one. It only tells you that reality contains something your current description does not capture completely. The theory must then catch up, and theories are built from patterns. So researchers will search for patterns: a second state, a related decay, a new interaction, a symmetry, a connection to dark matter, a deviation in Higgs behavior, a change in rare decay processes. Any of these could transform one anomaly into a larger structure, and if several of them appear together, the implications could be enormous. That is the cliff edge. One strange state is intriguing. A family of related phenomena is revolutionary, because then the question is no longer, what is this? It becomes, what entire sector of physics have we been missing? And that possibility takes us far beyond one collider. It reaches into the history of the universe. Imagine the early cosmos again, a universe so hot that the distinctions between the particles we know today may not yet have existed in their present form. Fields interacting, symmetries changing, particles appearing and disappearing, the vacuum settling into a new configuration. As the universe expanded, its temperature fell, the physical landscape changed, transitions occurred, matter became more structured. Eventually, the universe cooled enough for atoms to form, then stars, then galaxies, then planets, then life. Every stage depended on the rules established at earlier stages. If an unknown quantum state existed during one of those transitions, it could potentially have influenced what came afterward. Again, that is a possibility, not an established consequence, but it is one reason fundamental physics matters. We are not studying particles simply because particles are small. We are studying them because the rules governing the smallest scales helped shape everything that followed. Your body is made of atoms. Atoms are built from nuclei and electrons. Nuclei contain protons and neutrons. Protons and neutrons contain quarks and gluons, and the behavior of those particles traces back to quantum fields. The universe you can touch is connected to the mathematics CERN investigates underground. That is an extraordinary chain. But there is another scale shift still waiting, because if a new state is connected to the vacuum, then the question becomes cosmic. If it is connected to new particles, the question becomes astrophysical. If it is connected to new forces, the question becomes fundamental. And if it is connected to all three, we may be looking at something much larger than a single discovery, perhaps even a glimpse of physics beyond the standard model. Yet we must remain disciplined. The phrase "beyond the standard model" does not mean magic. It does not mean every strange result is revolutionary. It means physics that extends our current framework while reproducing the successful predictions we already trust. That extension has been expected for decades. The mystery is not whether new physics exists somewhere. Most physicists suspect that the standard model is not the complete description of nature. The mystery is where the new physics will appear, and how obvious it will be when we finally see it. Maybe it will arrive as a spectacular new particle. Maybe it will appear as a tiny deviation in a precision measurement. Maybe it will emerge as an unexpected quantum state. Maybe it will be connected to dark matter. Maybe it will reveal a symmetry nobody knew existed. Or maybe the strange signal will eventually disappear. That last possibility must remain on the table, because scientific integrity requires it. A mystery is valuable precisely because it has not yet been resolved, and this one cannot be resolved by language. It requires evidence. So the next phase of the investigation becomes broader. Researchers begin asking whether the same underlying physics could connect seemingly unrelated puzzles. Could it explain something in cosmology? Could it leave traces in the cosmic microwave background? Could it affect the formation of matter? Could it connect to the particles that make up dark matter? Could it influence the behavior of the Higgs field? Could astronomical observations provide an independent test? These questions take us from the underground tunnels of CERN to the largest structures in existence. From quantum states measured in fractions of a second to galaxies whose light has traveled for billions of years. And somewhere between those extremes may lie the real significance of the discovery. Because perhaps the strangest thing about quantum physics is not that the microscopic world behaves differently. It is that the microscopic world may be responsible for the universe we see, the galaxies, the stars, the planets, the chemistry of life. All of it emerged from an early universe governed by quantum rules. A change at the bottom of that chain can echo upward, and if the new state is real, those echoes are what scientists will search for next. But there is one final question before we can understand the larger implications. What if the signal does not belong to an isolated particle process at all? What if it is connected to a transition in the quantum fields themselves? Because then CERN may not simply have discovered a new object. It may have caught matter-changing phase, a glimpse of a new organization of reality, and that possibility would force us to reconsider something even more basic. Not just what particles are, but what a physical state actually means. The answer could reach from the deepest structures of quantum theory to the first fractions of a second after the birth of the universe. And that is where the story moves next. Away from the detector, away from the individual collision, toward the cosmic consequences. Because if this strange quantum state is truly new, the most important question may not be what CERN discovered underground. It may be what the universe has been doing with that same physics for billions of years. There is a strange habit we have developed as a species. We divide reality into categories. The very small belongs to particle physics. The very large belongs to astronomy. The distant past belongs to cosmology. The behavior of materials belongs to condensed matter physics. And somehow, because the names are different, we begin to imagine that these are separate worlds. They are not. There is only one universe, and the same physical laws operate across every scale. The atoms in your hand were shaped by forces that also govern stars. The particles inside those atoms were created from fields that existed in the early universe, and the structure of those fields helped determine what the cosmos would eventually become. That is why a strange quantum state at CERN could matter far beyond the laboratory, not because every microscopic discovery automatically changes astronomy. It doesn't. But because fundamental physics sits at the bottom of the cosmic chain. Change the rules at the bottom, and everything built on top of them has to be reconsidered. This is where the mystery becomes much larger. Suppose the unusual state really exists. Suppose repeated experiments confirm it. Suppose its properties cannot be reproduced by the standard model alone. Then the next question is unavoidable. Was this state merely something humans created, or has the universe been producing it naturally for billions of years? That question takes us back to the beginning. Not the beginning as a philosophical idea, the physical beginning. The early universe was an environment unlike anything we see around us today. It was hotter, denser, more energetic. Matter did not exist in the familiar forms we know now. There were no stable planets, no ordinary stars, no atoms arranged into molecules. The universe was dominated by radiation, particles, and fields. As space expanded, temperatures fell, and as temperatures fell, the universe passed through different physical regimes. This is one of the most important ideas in modern cosmology. The universe did not simply become larger, it changed state. Imagine water inside a freezer. At one temperature, it is liquid. Lower the temperature, and eventually it becomes ice. The molecules remain molecules, but the organization changes. the properties of the system change. The universe experienced transitions that were far more fundamental. The forces and particles we observe today may be the cooled remnants of a much more symmetrical early state. The Higgs field is part of that story. At high enough energies, the electroweak interaction can be described in a way that does not resemble the separate electromagnetic and weak forces we experience today. As the universe cooled, the Higgs field settled into its present configuration. Particles acquired masses through their interaction with that field. The universe became capable of forming increasingly complex structures. Eventually, atoms could exist, then stars, then galaxies, then planets. This is why a new quantum state could become more than a curiosity. If the state reflects an unfamiliar configuration of a field or an unusual interaction, perhaps related conditions existed during one of these ancient transitions. Perhaps the state is a modern laboratory glimpse of a phase the universe passed through long ago. That would be extraordinary, but we must be careful. A state created at CERN does not automatically prove that it existed in the early universe. The conditions are different, the timescales are different, the densities are different, and cosmological history depends on details that a collider cannot reproduce. The connection has to be demonstrated. Still, the possibility is worth investigating, because the universe leaves evidence behind. The oldest light we can observe is not merely beautiful, it is a record. The cosmic microwave background carries information about the early universe when it became transparent, roughly 380,000 years after the Big Bang. By then, the universe had cooled enough for electrons and nuclei to combine into neutral atoms. Photons could finally travel freely over enormous distances. Today, we detect that ancient radiation as microwave light. It fills the sky, almost uniformly, but not perfectly. Tiny fluctuations exist, minute variations in temperature and density. Those fluctuations became the seeds from which larger structures eventually formed. Galaxies, clusters, the cosmic web. The universe we see today grew from small differences in the early state, and that means the properties of fundamental particles can eventually influence structures spanning hundreds of millions of light years. The connection sounds impossible. It is real. The smallest scales can leave fingerprints on the largest. If a new quantum state altered the behavior of matter in the early universe, it might have affected how those initial conditions evolved. Again, this is not evidence that the state does. It is a question researchers could test. Could such a state change the expansion history? Could it alter the abundance of certain particles? Could it contribute to a phase transition? Could it interact with the Higgs field? Could it produce particles that survived long enough to become dark matter? Those questions bring us to one of the greatest mysteries in modern science: dark matter. Look up at a galaxy. The stars are moving, gas is rotating, galaxies orbit within clusters. And when astronomers calculate the amount of visible matter required to produce the observed gravitational behavior, something does not add up. There appears to be more mass than we can see. Something invisible contributes gravity. We call it dark matter, but the name is a placeholder. It tells us what the substance does. It does not tell us what the substance is, and that distinction has frustrated physicists for decades. Maybe dark matter is made of a new particle. Maybe it belongs to a hidden sector. Maybe it interacts extremely weakly with ordinary matter. Maybe it is something even more exotic. A confirmed new quantum state at CERN would not automatically be dark matter. That would be an extraordinary leap, but if the new state revealed a previously unknown particle or interaction with the right properties, researchers would naturally ask whether it could connect to the dark sector. This is how discoveries spread. One observation creates several possible doors. The next experiments determine which doors remain open. And dark matter is only one of them. There is another cosmic mystery. Matter itself. Everything you see is made from matter. The Earth, the Sun, your body, the distant galaxies. But the early universe should have produced matter and antimatter in closely related amounts, under many simple assumptions. When matter and antimatter meet, they can annihilate. If the universe had contained exactly equal quantities and everything proceeded symmetrically, much of the material we now depend on would have disappeared. Yet it did not. Matter survived. Stars exist. Planets exist. We exist. Some asymmetry must have occurred. Physicists know several ingredients that can produce matter-antimatter asymmetry, but the known mechanisms appear insufficient to explain the full cosmic imbalance. This is another crack in the picture, and it is another reason new quantum physics matters. Perhaps a previously unknown interaction could create additional sources of asymmetry in the early universe. Perhaps an exotic state could behave differently for matter and antimatter. Perhaps a new sector could participate in processes that left more matter than antimatter behind. Or perhaps none of these ideas has anything to do with the strange CERN state. At this stage, every connection is a hypothesis. But that is what hypotheses are for. They turn mysteries into experiments. The same thing happens with neutrinos. These particles are everywhere. Billions pass through every square centimeter of your body every second from the sun and other cosmic sources. They interact so weakly that most pass through Earth without stopping. Yet neutrinos have a remarkable property. They change type. A neutrino produced as one flavor can later be detected as another. This phenomenon implies that neutrinos have mass, and that fact alone tells us that the simplest version of the standard model is incomplete. Something has to be added. Perhaps the strange quantum state will have nothing to do with neutrinos. Perhaps it will. Again, the value lies in the connections. Physics is not a collection of isolated puzzles. The deeper theory has to explain all of them simultaneously. This is why researchers become excited when a new phenomenon appears. Not because one anomaly automatically solves the universe, because it might provide a new constraint, a new piece, a new direction. Imagine assembling a puzzle with thousands of pieces. For years, you have been unable to determine what belongs in one corner. Then you discover a piece with an unusual shape. It does not complete the corner, but suddenly several nearby pieces make more sense. That is what fundamental physics is often like. The most important discovery may not be the final answer. It may be the piece that tells us where to look. And now the story reaches another remarkable instrument, the James Webb Space Telescope. Webb operates nearly 1 million miles from Earth, around the Sun-Earth L2 region. Its segmented primary mirror spans about 6.5 meters. Its instruments are optimized for infrared observations. That allows Webb to study objects whose light has been stretched toward longer wavelengths by cosmic expansion. And that has given astronomers an extraordinary view of the young universe. Webb sees galaxies as they existed billions of years ago, not because it is literally looking backward in time through a window, because light takes time to travel. When Webb detects a galaxy more than 13 billion light-years away in observational distance terms, the light reaching its mirrors began its journey when the universe was vastly younger. The telescope is therefore not simply observing distant objects. It is reading cosmic history, and sometimes that history surprises us. Webb has revealed unexpectedly bright and mature-looking galaxies at early cosmic times. Some appear to contain substantial stellar populations surprisingly early. Some host actively feeding black holes. Some have structures that challenge simple assumptions about how quickly galaxies assembled. These observations do not mean the Big Bang model has collapsed. They mean our models of early galaxy formation may need refinement. That distinction is crucial, and it illustrates something about the scientific process. When a telescope sees something unexpected, astronomers do not immediately rewrite cosmology, they investigate. Could the galaxy be closer than assumed? Could its brightness be amplified? Could an active black hole contribute to the observed light? Could the stellar population be different from what models expected? Could the mass estimates be wrong? The same discipline used at CERN applies in space. Measure, test, compare, challenge, revise. That is why the combination of CERN and Webb is so intellectually powerful. CERN asks what matter does under controlled extreme conditions. Webb asks what the universe did with those physical rules. One creates, the other observes. One compresses enormous energy into tiny regions. The other collects faint photons that have crossed cosmic distances. Yet both are investigating the same reality. And this brings us to the cosmic web. On the largest scales, matter is not distributed randomly. Galaxies form enormous filaments. Clusters gather at intersections. Vast voids separate dense regions. The pattern resembles a web stretching across the observable universe. But the cosmic web began from tiny fluctuations, microscopic irregularities. Quantum fluctuations in the early universe may have been amplified as the universe expanded. Over billions of years, gravity transformed those small differences into immense structures. A fluctuation that was once unimaginably tiny could eventually become the seed of a galaxy cluster. That is one of the greatest scale shifts in physics. Quantum uncertainty can become cosmic architecture. Something smaller than an atom can influence structures larger than galaxies. And that means the phrase quantum state should never make us think only about laboratories. Quantum physics is not confined to the microscopic. The entire universe is quantum at its foundation. The question is how those quantum rules become the classical reality we experience. If a new state reveals a previously unknown property of quantum fields, it could potentially help us understand some part of that transition. Perhaps. But again, the evidence would have to be built. This is where fundamental physics becomes humbling. We can imagine connections far faster than we can prove them. A theoretical idea can be beautiful in an afternoon. An experimental confirmation may take 10 years, sometimes longer. The universe moves slowly. Science must wait. And this is especially true when the phenomenon being investigated is rare. Suppose the strange state appears once in every billion relevant collisions. Producing enough examples to study its properties could require enormous datasets. Then researchers need to determine whether those events share the same characteristics. Do they cluster at the same energy? Do they decay into the same particles? Do they have the same angular distribution? Does their rate increase with collision energy? Does another experiment observe them? Does the phenomenon disappear under different selection criteria? Every answer adds another piece, and every failed prediction eliminates another theoretical possibility. This is how the unknown becomes measurable. One parameter at a time, one collision at a time, 1 year at a time. There is also another fascinating possibility. The new state might not be stable. In fact, it probably would not be. Most exotic states produced at high energies are extremely short-lived. They decay almost immediately. That means the state itself may never travel far enough to be seen. Its descendants are what researchers detect: a photon, a lepton, a jet of hadrons, missing energy, a combination of particles. From these products, the original event is reconstructed. This creates a strange philosophical situation. Scientists can become confident that something existed even though they never observed it directly. They observe its effects. That is how much of modern physics works. We do not see the quantum field, we infer it. We do not see dark matter directly. We infer its gravitational influence. We do not see the interior of a black hole. We infer properties from the region around it. Science is often the art of turning consequences into knowledge. And the more indirect the observation, the more carefully the inference must be tested. That is why independent evidence matters. If a new state affects another process, researchers can search there. If it exists in the early universe, cosmologists can ask whether it leaves an observable imprint. If it interacts with known particles, collider experiments can measure the coupling. If it produces a stable particle, underground detectors may eventually search for it. One discovery can therefore create an entire experimental ecosystem. That is how the frontier expands. But there is a darker possibility. What if the new state is not part of a larger theory that elegantly explains our mysteries? What if it is simply another strange piece, another particle, another state, another number in an increasingly complicated model? Would that be disappointing? Perhaps. But science does not choose discoveries for aesthetic reasons. Reality may be simple, or it may be extraordinarily messy. Nature owes us elegance, and if the universe turns out to be more complicated than our theories, our job is not to simplify it artificially. Our job is to describe it accurately. Still, physicists search for deeper simplicity. They look for symmetries. Symmetry is one of the most powerful ideas in modern physics. A symmetry means, roughly, that certain transformations leave the underlying laws unchanged. Rotate a perfect sphere, and it remains a sphere. More abstract symmetries govern particle interactions. They determine what kinds of particles can exist. They constrain how those particles interact, and they can produce conservation laws. A new quantum state might reveal a symmetry we did not know was present, or it might show that an expected symmetry is broken in an unexpected way. That would be profound, because symmetry is not just mathematical decoration. It is part of the architecture of physical law. The standard model itself is built around symmetries. The Higgs mechanism is deeply connected to how those symmetries behave, and the early universe may have undergone several symmetry-breaking transitions, as it cooled. So a new quantum state could potentially become a clue about the universe's deeper architecture. But there is an important limitation. A single experimental result cannot tell us which architecture is correct. Nature does not reveal the blueprint all at once for us. It gives us pieces, sometimes tiny pieces, sometimes contradictory pieces, and humans try to assemble them. That is why the next generation of measurements matters so much. More luminosity, more collisions, better detector performance, improved theoretical calculations, more precise simulations, and eventually, perhaps, entirely new machines. The future of particle physics may depend not only on discovering heavier particles, but on measuring familiar ones with extraordinary precision. Sometimes the doorway to new physics is not a spectacular object. It is a disagreement in the 6th decimal place. That possibility makes the current era unusual. We have enormous machines, sensitive telescopes, powerful computers, sophisticated detectors, and theories developed over more than a century. Yet some of the most fundamental questions remain open. What is dark matter? Why does matter dominate antimatter? What happens to information in black holes? How does gravity become quantum? Why do physical constants have the values they do? What happened during the earliest moments of cosmic history? And perhaps now another question joins them. What exactly is this strange quantum state? If the observation survives, that question may become one of the most important questions in experimental physics. But even then, the answer may not come quickly. The first confirmed measurement could be followed by years of characterization. Researchers may discover that the state has relatives. They may find an entire family, or they may discover that it connects to something already known, or they may find that the original interpretation was wrong. Science must remain open to every possibility, and that is why we should resist the temptation to declare that current physics has failed. Physics has not failed. Physics has reached a boundary. There is a difference. A map is not wrong because it ends at the edge of the territory. It is simply incomplete. The standard model may be exactly that, a map that is astonishingly accurate across an enormous region of reality. But beyond its borders, something else may exist. The possibility is both exciting and humbling, because every time humanity expands its map, the unknown does not disappear. It gets larger. We thought Earth was the center. Then we learned Earth orbits the Sun. We thought the Milky Way was the universe. Then we discovered other galaxies. We thought stars were the largest structures worth understanding. Then cosmology revealed the cosmic web. We thought matter was composed of atoms. Then atoms opened into nuclei, quarks, fields, and quantum states. The pattern continues. Every answer becomes a doorway. And perhaps the strange CERN state is another doorway. Not necessarily the final one, perhaps not even the most important one, but potentially a new opening in the wall. The most intriguing possibility is that the state could connect several puzzles that currently appear unrelated. dark matter, the Higgs sector, matter-antimatter asymmetry, early universe physics, quantum fields. If even two of these mysteries turn out to share a common cause, the significance would grow enormously. If several connect, the discovery could become transformational. But there is still a final test. Nature must reproduce the phenomenon, again and again, and somewhere else. That is the difference between a strange result and a new chapter in physics. The universe has no obligation to repeat itself, but physical laws should. If researchers understand the state correctly, they should eventually be able to predict when it appears, how it behaves, and what else should accompany it. The moment a mysterious observation begins making successful predictions, it stops being merely mysterious. It becomes physics. And that is the threshold we are approaching. The signal has survived enough scrutiny to demand attention. The theoretical explanations remain divided. The possible implications reach from quantum fields to cosmic history, and the universe, for now, is refusing to tell us which explanation is correct. That uncertainty is not the end of the story. It is the most interesting part, because the next stage is no longer about asking what the state could mean. It is about asking what happens when scientists try to reproduce it, measure it, and follow its consequences. If the state is real, it may have a signature beyond CERN, a footprint in the behavior of known particles, a clue in the early universe, perhaps even a connection to one of the greatest mysteries in modern cosmology. And if those connections begin to appear, then the strange signal we started with will no longer look like an isolated anomaly. It will look like the first visible piece of a much larger structure, a structure that may have been hiding in the equations all along, waiting for an experiment powerful enough to expose it. There is a strange point at the end of every scientific discovery when the excitement begins to disappear. The graphs remain, the equations remain, the measurements remain, but the first rush of possibility fades. And what is left is something quieter, questions, more questions than answers. That may be the most honest way to end a story about a new quantum state, because if the observation is real, it does not give us permission to pretend we understand it. It gives us a reason to keep looking. That distinction matters. A discovery is not the moment humanity suddenly knows everything. It is the moment something becomes impossible to ignore. And that is where CERN has repeatedly changed the history of physics. For decades, the laboratory has pushed matter into conditions that ordinary experience cannot reach. The Large Hadron Collider stretches for roughly 27 kilometers beneath the ground near Geneva. Its proton beams travel at speeds extremely close to the speed of light. Its experiments record enormous numbers of collisions, and from those collisions, scientists reconstruct events that existed for fractions of a second. That is the remarkable thing about particle physics. Human beings cannot hold these states in their hands. We cannot watch them with our eyes. We cannot place them inside a glass container. We create them briefly. We measure their effects. Then they are gone. And yet those fleeting events can tell us something about the entire universe. If a new quantum state has truly emerged from this environment, it would be another example of that strange relationship between the microscopic and the cosmic. A tiny event, a huge question. But now comes the part that matters most: confirmation. No matter how beautiful the signal looks, no matter how persuasive the theoretical explanation becomes, the scientific community has to ask whether the result can survive repetition. This is where many apparent discoveries have disappeared. A small excess can become smaller with more data. A promising interpretation can fail when another decay channel is measured. A statistical fluctuation can fade. A detector effect can be uncovered. A calculation can be corrected. And suddenly the mystery is gone. That is not failure, it is progress. Science does not advance only when new particles are found. It advances when false explanations are eliminated. Every time an experiment rules something out, the map of possible reality becomes smaller. And sometimes a smaller map is more valuable than a spectacular claim. Imagine trying to locate an unknown city on an enormous continent. At first, the entire continent is possible. Then one survey rules out the northern half, another rules out the west. Another eliminates several mountain ranges. You still have not found the city, but you know where it cannot be. Eventually, the search area becomes small enough that the remaining possibilities become meaningful. Fundamental physics works in much the same way. A new quantum state would therefore be only the beginning. Researchers would want to know its mass or energy, its spin, its lifetime, its charge, its production rate, its decay products, its interaction strengths, its behavior under different collision conditions, and whether related states exist. Each measurement would transform the mystery. At first, something happened. Then, something with these properties happened. Then, this state interacts in this way. Then, it belongs to this family. And eventually, perhaps, we understand why it exists. That final step can take generations. Sometimes physics moves quickly. Sometimes nature refuses to cooperate. Consider the Higgs boson. The theoretical mechanism had been discussed for decades before the particle was observed. The 2012 announcement was historic, but even after the discovery, researchers did not suddenly understand every aspect of the Higgs sector. They had found the particle. Now they had to measure it. That is an important lesson. Discovery opens the door. Precision tells you what is behind it. A new quantum state would face that same journey. And the first major question would be whether it is truly new. That sounds obvious. It is not. A phenomenon can be new to an experiment without being new to nature. It can be a previously predicted state finally observed. It can be a known state appearing under unusual conditions. It can be a composite arrangement of familiar particles. It can be an emergent phase. It can even be an artifact of analysis. The word new, therefore, has to be earned. That is why scientists compare observations against the full history of previous experiments. If another detector has already seen something similar, the interpretation changes. If another experiment sees nothing, the mystery becomes more complicated. If independent facilities reproduce the same result, confidence rises. If future measurements reveal additional related states, the significance could increase dramatically. And if no one can reproduce it, the original result may eventually become a footnote. This is the uncomfortable truth behind every exciting headline. The universe gets the final vote. Not the headline, not the scientist, not the journalist, not the audience. Nature. That is why CERN's role is so important. It does not merely produce spectacular results. It produces opportunities for reality to disagree with us, and that disagreement is valuable, because the greatest scientific discoveries often begin as disagreements. Something does not match, a number is wrong, a trajectory is unexpected, a spectrum contains an unexplained line, a particle appears where it should not, an ancient galaxy seems too mature, a quantum state behaves differently. Each anomaly is a question mark. But not every question mark becomes a revolution. Some disappear, others grow. The mystery we have followed belongs to the second category, only if the evidence continues to strengthen. And that is the point where we need to separate what is known from what remains unknown. What do we know? We know quantum mechanics successfully describes microscopic phenomena across an enormous range of experiments. We know the standard model accurately predicts a vast number of particle interactions. We know CERN has repeatedly created and studied particles and states that cannot be produced under ordinary conditions on Earth. We know the standard model is incomplete as a description of all physical reality. We know dark matter remains unidentified. We know neutrinos have mass and that the simplest standard model does not fully accommodate their observed behavior. We know matter dominates the visible universe. We know general relativity and quantum mechanics are not yet unified into a complete theory of quantum gravity, and we know that experiments continue to search for phenomena that could reveal the missing pieces. What we do not know is much larger. We do not know the ultimate identity of dark matter. We do not know whether there are undiscovered fundamental particles. We do not know whether additional forces exist. We do not know whether the standard model's missing physics will appear at collider energies, in precision measurements, in astrophysical observations, or somewhere completely unexpected. And if the particular quantum state described by our story is confirmed, we still would not immediately know what deeper theory it belongs to. That is the honest boundary, the boundary between measurement and interpretation. And perhaps that boundary is where science is most beautiful, because there is something profoundly human about looking at the universe and admitting, we don't know yet. Not ignorance, not surrender, a deliberate refusal to pretend. For thousands of years, human beings looked at the night sky and saw lights. We gave them names, we created stories, we tried to understand their movements. Then mathematics entered the picture. Telescopes followed, photography, spectroscopy, spacecraft, particle accelerators, and eventually instruments capable of detecting individual traces of subatomic events. The scale of our curiosity expanded, but so did the mystery. The James Webb Space Telescope is a perfect symbol of that process. Webb can collect infrared light that has traveled across cosmic distances. Its 6.5-meter segmented mirror allows it to observe extraordinarily faint objects. It can study galaxies from the early universe. It can examine stellar nurseries. It can investigate atmospheres of exoplanets. It can look at the distant past. And yet every new image raises another question. A more distant galaxy, an unexpectedly complex structure, a population of stars, a black hole growing earlier than expected, a chemical signature. The universe keeps answering one question by creating another. CERN does the same thing underground. The collider creates an interaction. The detector records the result. The result becomes a measurement. The measurement becomes a theory. The theory creates predictions. The predictions become experiments. And then the cycle begins again. That cycle is not a sign that science is failing to reach an ending. It is what scientific progress looks like. There may never be a final experiment that answers every question. There may never be a final equation that closes the book, because every deeper layer of reality can expose new structure underneath it. We once thought atoms were indivisible. Then we discovered nuclei, then quarks, then quantum fields. Now ask whether fields themselves are part of an even deeper description. Maybe they are, maybe they are not. We do not know. And that uncertainty becomes especially powerful when we consider the early universe. The universe we see today is the result of an unimaginably long physical history. Roughly 13.8 billion years ago, the observable universe was in a vastly hotter and denser state. Over cosmic time, expansion changed the environment. Particles interacted, nuclei formed, atoms formed, stars ignited. Galaxies assembled, black holes grew, planets formed, chemistry became complex, and eventually, on at least one planet, matter became capable of asking where it came from. That may be the strangest part. The universe produced observers capable of studying the universe, and now those observers are building machines underground to reproduce tiny fragments of conditions that existed billions of years ago. CERN is part of that story. So is Webb. So are the countless observatories, laboratories, detectors, and theoretical calculations built by generations of scientists. Each is another way of asking the same question. What is reality made of? We often imagine that question as though it has a simple answer. Atoms, particles, fields. But each answer creates another layer. What are atoms made of? What are particles? What is a field? Why do fields have these properties? Why do the constants of nature have these values? Why does the universe exist in this particular configuration? The new quantum state, if it survives, may not answer those questions, but it could tell us where one of the answers begins. That is enough. A compass does not need to show the entire landscape to be useful. It only needs to point somewhere, and a strange experimental result can function as a compass. It tells scientists, look here, measure this, try this explanation, build this experiment, search this energy range, look for this decay, test this symmetry, compare this prediction. A discovery becomes powerful when it changes what researchers do next. That is how we should judge the importance of a new quantum state. Not by how dramatic the headline sounds, by how many new experiments it makes possible. If the state can be produced repeatedly, it becomes a laboratory object. If its properties can be measured precisely, it becomes a physical system. If theories can explain it, it becomes part of a larger framework. If those theories predict additional phenomena and the experiments confirm them, the discovery begins to reshape physics. That is the chain: observation, confirmation, characterization, prediction, verification, understanding. We are still near the beginning, and perhaps that is exactly where we should remain for a moment. Because there is a temptation, especially in science documentaries, to take an unexplained observation and race toward the biggest possible conclusion. New universe, broken physics, hidden dimensions, a theory of everything. But reality is usually more interesting than the exaggeration. The real story is slower. A detector records something strange, a researcher notices, a team checks it, another team analyzes it, a theorist proposes an explanation, someone else finds a problem with that explanation. More data arrive, the signal strengthens or weakens, a new experiment is designed, and years later perhaps, the scientific community knows what happened. That slow process may not sound as dramatic. It is more dramatic, because every step is earned, and if the strange state survives all of it, the final discovery will carry the weight of all those failed explanations behind it. That is when the phrase new physics will mean something, not because someone used the words, because nature forced us to use them. And imagine what that would feel like. Somewhere inside a control room, after years of uncertainty, a new dataset arrives. The researchers compare it with the prediction. The unusual structure appears again. Different energy, different dataset, same behavior. The numbers line up. The alternative explanations become increasingly difficult to maintain. The state is there, again and again. For the first time, the scientific community is no longer asking whether the phenomenon exists. They are asking what it means. That would be a remarkable moment. But even then, the universe would not suddenly become simple. Instead, the horizon would move. New questions would appear. Does the state have partners? Does it interact with the Higgs field? Does it connect to dark matter? Does it reveal a hidden symmetry? Does it appear in other experiments? Could it have existed in the early universe? Could its properties influence cosmological evolution? Could it point toward a larger theory? Could it eventually help bridge quantum mechanics and gravity? These questions could occupy physicists for decades, and perhaps future generations will look back at the first signal the way we now look back at earlier discoveries. As the beginning, not the answer. The beginning. There is something fitting about that, because the universe itself is unfinished from our perspective. We see one chapter, we do not see the entire book. The cosmic microwave background gives us an image of the universe when it was only about 380,000 years old. Webb allows us to see galaxies from the first few 100 million years of cosmic history. CERN lets us recreate tiny pockets of extreme energy. Different instruments reveal different pages. None gives us the whole story, and perhaps no single instrument ever will. That does not make the search pointless. It makes the search human. We are creatures on a small planet orbiting an ordinary star. The Milky Way contains hundreds of billions of stars. The observable universe contains an enormous number of galaxies. And yet, from this tiny world, we have built machines capable of asking questions about the fundamental structure of reality. That is extraordinary. The same atoms that formed stars eventually assembled into brains. Those brains learned mathematics. Mathematics became equations. Equations became predictions. Predictions became machines. Machines became measurements. And measurements became knowledge. The universe is, in a strange sense, investigating itself. Maybe that is the deepest lesson. The point of discovering a new quantum state is not simply to add another entry to a catalogue of particles. It is to discover another piece of the language in which reality is written. And perhaps that language is larger than we currently imagine. Maybe the Standard Model is one chapter. Maybe quantum field theory is one layer. Maybe there is a deeper framework beneath it. Maybe the universe is ultimately elegant. Maybe it is not. We cannot decide. Only nature can. And that brings us back to where this journey began. A signal, a strange pattern, a possibility, something that appeared to sit just outside the comfortable boundaries of existing physics. We asked what it was. We asked whether it was real. We asked whether known physics could explain it. We followed the possibilities into quantum fields, exotic states, particle interactions, the early universe, dark matter, symmetry, and cosmology. And now we arrive at the most honest answer. We do not know. Not yet. If the state is confirmed, it may become one of the clues that leads physics beyond the Standard Model. If it is not, the investigation will still have taught us something. Either way, the experiment has done its job. It has asked nature a question, and nature has answered with enough complexity to make us ask another. That is not disappointment, that is discovery, because the frontier of science is not the place where all mysteries disappear. It is the place where our questions become better, and perhaps somewhere beneath the ground at CERN, inside another collision that lasts for less time than a blink, the next clue is already waiting. A different energy, a different pattern, a different decay, another small disagreement between theory and reality. Maybe it will be nothing. Maybe it will be a fluctuation. Maybe it will be an error. Or maybe, one day, the detectors will record something so persistent that we will have no choice but to change the map again. And if that happens, the words will probably sound surprisingly ordinary. Another measurement, another analysis, another result. But behind those quiet words will be something enormous. The realization that reality has once again exceeded the boundaries of human expectation. That is what CERN ultimately gives us. Not certainty, a confrontation. A chance to put our most beautiful theories in front of the universe and ask whether they are true. Sometimes nature agrees, sometimes it disagrees. And when it disagrees, we listen. Because somewhere inside that disagreement may be the next revolution, the next Einstein, the next theory, the next machine, the next generation staring into a dataset and realizing that the universe has been trying to tell us something for a very long time. We simply weren't ready to hear it until now. And perhaps that is the most remarkable thing about the quantum world. It does not care how strange an idea sounds. It does not care what seems intuitive. It does not care how elegant our equations are. Reality is under no obligation to make sense to us. Our task is harder. We have to make sense of reality, piece by piece, measurement by measurement, question by question. And somewhere between the smallest quantum state and the largest galaxy, we may eventually discover that they were never separate mysteries at all. They were different reflections of the same universe. A universe that began in conditions we can barely imagine, expanded for billions of years, filled itself with stars, created worlds, and eventually produced beings capable of building a machine beneath the earth to ask what everything is made of. Perhaps the answer is waiting inside the next collision. Perhaps it is hidden in the light of an ancient galaxy. Perhaps it is encoded in the dark matter surrounding a galaxy we cannot see directly. Perhaps it lies in a theory nobody has written yet. Or perhaps the universe has another surprise waiting beyond all of them. We don't know. and for now that is enough. Because the unknown is not an empty space, it is where the next discovery lives.